Hey, welcome back. Today we have a quick one. We have a small problem. We have timing belt gear blanks, like this one, and we need to bore them to 5H7. That's not a problem. 5H7, we have a reamer for that, not a big deal. But the tolerance for concentricity between this bore and the profile of the hopped section is fairly tight. 20 micron in this case. Looking at it, you might say, well, I'm just going to grab it here with a collet because probably this and this has been machined in the same setup, and that will be the way to go. And the problem is it's not. These are made in a different way. These get hopped as a long bar, then parted off, and then this this bigger ring here is pressed on. You can see the seam here all around. Means the concentricity between the hopped timing belt gear profile and the OD here is not defined, at least not for a very close tolerance. So, well, that's a problem. Also, we can't grab it on this profile with a collet because we have this rim here. What we could do is we could use soft jaws and put a groove in it for this rim here, so the soft jaws clear this rim. That would work very well. Or what we can do is we can make some clamshells, a clamshell clamp situation here. This started out as a ring, one full ring, was turned ID and OD in the same setup. I micrometered the OD over the teeth on several of these gear blanks and found an average, and then I bored this ring to this ID, checked it with gauge pins, and the OD is just turned clean, so it runs true to the ID. Part it off, and then using a slitting saw, cut a part in the center and very carefully deburred. And the idea is you put these two clamshells on here, then you go to your lathe, then you either put it in a collet chuck, or what I do, I'm holding it in a 6-jaw chuck on my lathe. And then we can drill, bore, and ream it. So let's go to the machine and look at the procedure in detail, or in reality. We're over at the lathe, 6-jaw chuck here. We have our clamshell to hold this gear blank, and we put it in here in a way the split is of course between the jaws. Otherwise it wouldn't make too much sense. And when I clamp it, I make sure to leave about 3 to 4 millimeters of the clamshell stick out to the front, and there is a reason for that. Tighten it down with a defined gronk. I take my indicator and I bring it in. And now we can indicate on the OD of the clamshell, and since the ID and OD of the clamshell is turned in the same setup and is making full contact to the teeth of the timing belt gear, this gives us a very exact indication with the indicator when we indicate the runout. So we zeroed out the dial test indicator here, and now we can check it. Starting at 0, makes a little bit of a jump, of course, in the area of the split, but this is darn good. This is well within 10 micron. Since this chuck is adjustable with the set screws here on the back, out here, this is adjustable for runout. I could tram it in if it was off, but since I since I adjusted the first one, and I'm always using the same pinion on the chuck. I'm always using the one marked here with a 0. I get consistent run out over the entire run of these parts. There is nothing magical about the pinion with the 0. It's just a marker with which the chuck was tightened when it was bored, when the hard jaws were bored. And when I rebored the jaws, that's also the reason why there are pinholes in the face of these jaws, so I could hold a ring and preload the jaws for boring. I also used the 0. So each time I use the 0, I get the best run out without having to mess with the run out setting. Of course, over the range of the chuck, or the clamping range of the chuck, there is tolerance, and it will not be 0, but it will be close. So that's everything about the 0 pinion that you need to know. So we got our run out pretty decent. It's clamped securely. And now for the machining, we could just drill and ream it and then be surprised how bad it will be. So let's do it properly. There is a small drill. This is a 4mm drill. We need 5mm nominal as a final dimension. So 4mm drill to rough out most of the material. Okay. Then we have a tiny boring bar, just to clean up the bore and get it to 4.9 millimeters. Okay, that's 4.9 now. Now we come back with drill chuck. The boring bar is too short to reach all the way through this pinion. So I have a 4.9mm drill here, which will remove the last few millimeters of the hole. Since there is a lot of guidance now through to the pre-bored hole, the drill will run through. Then we need a countersink. And for reaming, we are in the lucky position to have a floating reamer holder. This allows to negate any misalignment between the tool and the bore, since it allows a parallel shift of the tool. There we go. And that's how you do a precision bore in a timing belt gear that you can not access easily on the OD. This one also needs some turning work done to it. Okay, and that's the precision work done to a timing belt gear that you cannot easily clamp on the OD of the gear profile. Clamshell, that's the trick. Put them in a small bag, label it with the gear profile and the tooth number, and you have a tool that you can reuse. This, for example, is for a T2.5 16 teeth timing belt gear. How to inspect? I have a go, no-go gauge for the 5H7 fit, which is a 0 on both sides, which fits. And the no-go side is plus 12. This is 12 micron oversize. So this doesn't go, and shouldn't on this side either. Doesn't. Nope. No go. Oop. You have to be a little bit careful on aluminum with the no-go gauge because you can push up a burr. So then I have a 5.00 millimeter gauge pin here held in a V-block, so it's standing out horizontal. I can put the timing belt gear on here, and I bring in an indicator. And I will just find the high spot of one of the gear teeth and manipulate the indicator to a convenient number, like here, 40. Now I can just indicate the gear or each tooth. I have to be a little bit careful because I have some slop on the shaft, of course. Since the bore is not 5.000, it's 5.008 maybe, 8 micron or something like that oversize. But in general, this gives a good idea about the run out. So it's pretty much within 10 micron, considering this indicator. Slightly over. We have 20 micron of tolerance here. So that's how you check the concentricity of this. Another way would be to put a short piece of a gauge pin in here and measure off the flanks of this gear profile. But since this is a hopped profile where not only the root is cut, but also the crest is cut in one go, we can indicate it like this. No need to cut down a gauge pin for this one. Or use a small gauge pin, a dowel pin would also work if you find one with the right diameter. Or a piece of a high-speed steel punch. While we're here, we could also look at how I cross-drill these pulleys. Since I have in total 22 of them to do, I decided to use the punch grinding fixture on my milling machine, just holding it in grinding wise. I'm using the punch grinding fixture because it's extremely fast to index. I have the stop pin here, and I set the stops to 90 degrees, so it's very fast to go from first hole to the second hole. It's quite a bit faster than the large heavy-duty indexing head of the milling machine itself. Also, the V-block here is a very good way to hold the pulley with the clamshell for drilling. It's a very precise way. Instead of the regular C-clamp that comes with the V-block, I'm using a parallel clamp because it doesn't project up as far above the work, and I have more clearance for a spotting drill and a regular drill in both orientations. These clamps here are traditionally very much in the way. So the design says 90 degrees apart, and it's an M2.5 thread. So we're drilling on this machine, and then we go to the drill press and we do the tapping, power tapping. So let's go. Okay, let's change parts. Parallel clamp comes off, part goes out, the clamshell comes off, of course. Clamshell goes around the part. V-block gets cleaned, part goes in, then we add the C-clamp, or the parallel clamp, sorry, not C-clamp. So, and to set the end stop, or the X position, I have a gauge block here and a magnet. And I just hold the gauge block up against the face of the V-block, and I push the part out against the magnet, and it acts as a work stop. And then I can tighten down my parallel clamp back here, and I'm in position, or the part is in position. I can come back with my spotting drill. I really like the punch grinding fixture for doing very fast drilling or indexing for drilling. We don't need the immense precision that this fixture has for this kind of work, but the ease of indexing is here paramount. So part comes out. And now we go to the drill press and to the tapping. This looks like a very busy setup, but it's in reality not. I have my Tapmatic tapping head with a M 2.5mm tap in here. I have a thin V-block held in a vise, clamped to the table of the drill press, and I'm holding a 5mm carbide pin, which is in fact an end mill. And that's the whole setup. The parts go on the carbide pin, and in combination with the tap entering the hole, this aligns the part automatically, basically. When I set it up, I placed it in a way so the pin is kind of in line with the tap. It's not super critical because these Tapmatics have quite a bit of wiggle and give to them, so the tap can follow the hole despite not being lined up perfectly. I'm running relatively slow, and I also have the clutch of the Tapmatic set very lightly so I don't break a tap. And also I'm using a little bit of cutting oil, and between each hole I will blow off the chips from the tap. With small taps and machine tapping, this is extremely important, otherwise the tap will bind up and give you very much problem. So let's turn on. I'm running at 180 RPM. With the Tapmatics, you want to set the depth by using the depth stop of the drill press and not the clutch. The clutch on the Tapmatic heads is only to prevent breakage due to over-torquing the tap, not for running into the bottom of a non-through hole. In this case, I set the depth stop, so I'm now at my lower end of the depth stop, and the tap pulls itself out of the Tapmatic a little bit further until here, and this is my final depth where the tap will stop. Then it will just make a little bit of a clicking noise when it jumps over the clutch or the face coupling in there, not the friction clutch. The friction clutch is only to prevent breakage, and the face coupling, or the gear coupling more or less, is for setting a depth stop. That's some hints on machining timing belt gears. Thank you all for watching, and I'll be back.